Hello friends, in previous class we have obtained an expression for potential at a point due to a charge, and today we shall obtain an expression for potential at a point due to a dipole. The point, it is a general point, it is neither on axial line or bisector. Therefore, potential at any point due to a dipole. And we have studied potential at a point due to a charge is phi equal to kq upon r. Potential due to a charge is inversely proportional to distance of the point from the charge, and k is Coulomb's constant, and it is equal to 1 upon 4 pi epsilon naught. And in the first chapter you have studied dipole. Dipole is a system of two equal and opposite charges separated by a small distance. This is a dipole. It has two equal and opposite charges, that is plus q and minus q, separated by a small distance 2a. And any point along the axis of the dipole is called axial point, and any point on the bisector, it passes through the center of dipole and is called bisector of dipole. And in the first chapter we have obtained an expression for electric field on the axis of a dipole as E equal to 2 kp upon r cube. Here intensity is inversely proportional to cube of the distance of the point from the center of dipole. It is on the axial point, and on the equator electric field on the equator or bisector is equal to minus kp upon r cube. And today we shall obtain an expression for electric potential at any general point about the dipole. And total charge on a dipole is equal to 0. Because minus q plus q, total charge, that is equal to 0. But it has a dipole moment is given by P equal to dipole moment P equal to Q into dipole length, charge into dipole length. The product of either of the charge and dipole length is called P is dipole moment, and dipole moment is defined as the product of either of the charge and dipole length. Now consider a dipole AB having charges minus q and plus q separated by a small distance 2a, that is AB equal to 2a. Let P be any point at a distance r from the center of dipole, and BP and AP are the distances of the point P from positive charge and negative charge. Let R1 and R2 be the distances of the point from negative charge and positive charge. Therefore, from the figure, AB is equal to 2A, that is dipole length. AP equal to R1, it is the distance of the point P from minus charge, minus Q, and BP is the distance R2, that is equal to distance of the point from positive charge. And let Phi1 and Phi2 be the potentials at point P due to negative charge and positive charge. Therefore, the total potential at P due to a dipole is equal to the sum of potentials at P due to negative charge and positive charge. Thus, if phi is the potential at point P, then phi equal to phi1 plus phi2, where phi1 is the potential at P due to negative charge and phi2 is the potential at P due to positive charge. Thus, but we know that potential at a point is given by, due to a charge is given by K Q upon R, where R is the distance of the point from the charge. Therefore, phi1 is the potential at P due to negative charge, and potential is given by KQ upon R. Here, and potential due to negative charge is negative, and for positive charge it is positive. Hence, phi1 equal to minus K into minus Q, that can be written as minus KQ upon R1, it is the distance of the point P, plus phi2 is potential at P due to positive charge, and that is equal to KQ upon R2, where R2 is the distance of the point from positive charge. And here KQ is common. Taking common, we get KQ in the bracket minus 1 upon R1 plus 1 upon R2, and it can be written as plus 1 upon R2 minus 1 upon R1. That is phi equal to KQ in the bracket. Here LCM is R1 R2, and here deficiency of R1, therefore write here R1 minus, here in this term there is deficiency of R2. Hence R1 minus R2 upon R1 R2. Take this as equation 1. Now find what is R1 minus R2 and R1 R2. Now draw BC perpendicular to AP. BC perpendicular to AP. Then BP is equal to CP is equal to R2. BP equal to CP equal to R2, and AC is equal to AP minus CP, where AP equal to R1, CP equal to R2. Therefore, AC equal to AP minus CP. That is AC equal to AP equal to R1 and CP equal to R2. And also, if point P is at far off distance compared to the dipole length 2A, then that is, if R is very greater than 2A, then R1 is equal to R2. If distance is very small compared to the point P, then distance from the center of dipole, that is R, is equal to R2 is equal to R1. Hence, R1 is equal to R2 is equal to R. And from the triangle, right angle triangle ABC, cos theta equal to, here theta is the angle made by the line joining the point P and the dipole. dipole length. This is the theta. Therefore, this angle is also equal to theta. From the triangle ABC, cos theta equal to base upon hypotenuse, that is AC upon AB is equal to cos theta. Therefore, AC equal to AB cos theta. And here AC equal to R1 minus R2. AC equal to R1 minus R2. Therefore, R1 minus R2 is equal to, and AB equal to 2A cos theta. Hence, R1 minus R2 equal to 2A cos theta. Now, substitute these values in equation 1. We get phi equal to KQ into R1 minus R2 is equal to 2A cos theta upon R1 R2. Here R1 is equal to R2 is equal to R if the point is at far off distance. Hence R into R is equal to R square. And according to the definition of dipole moment, P equal to K into 2A, that is Q into 2A. Therefore, P equal to Q into 2A is called dipole moment. Hence, it can be written as K P cos theta upon R square. This is the expression for potential at any point due to a dipole. Or it can also be written as phi equal to 1 upon 4 pi epsilon naught. Here K is Coulomb's constant and its value is 1 upon 4 pi epsilon naught into P cos theta upon R square. Clear? Again, here theta is the angle between line joining the point P from the center of dipole and the dipole moment P. Therefore, here theta gives the direction of potential at P. Hence, cos theta, it can be written as R cap. I interchange this. That is phi equal to 1 upon 4 pi epsilon naught into P cos theta. It gives the direction of potential at P, that is R cap upon R square. Here R cap represents the direction of potential at P. And theta is the angle between line joining the point P and dipole moment, and dipole moment is always from negative charge to positive charge. And also we know that R cap is equal to factor R upon magnitude of factor. We have studied magnitude of factor in PUC first year, that is factor R upon magnitude of factor R. Therefore, this can also be written as phi equal to 1 upon 4 pi epsilon naught into P upon R cube. This R square into magnitude of R, that is equal to R cube into R vector. Therefore, this dipole moment P and R, they are vectors. Therefore, potential at any general point due to a dipole is phi equal to 1 upon 4 pi epsilon naught into dot product of dipole moment and factor R upon R cube, or it is equal to 1 upon 4 pi epsilon naught into P vector dot r cap upon r square, or phi equal to 1 upon 4 pi epsilon naught into p cos theta upon r square. And simply we can write phi equal to kp cos theta upon r square. Kp cos theta upon r square, where potential at any point due to a dipole is inversely proportional to square of the distance of the point from the midpoint of dipole. Clear? And now we shall discuss the contrast between potential at a point due to a single charge and due to a dipole. Special cases. The potential at any point due to a dipole is given by phi equal to kp cos theta upon r square. This potential, it is for any general point. Then what is the potential on the axial line of a dipole? Consider this is the dipole, minus q and plus q, separated by distance 2a, and O be the midpoint of dipole. Any line passes through the dipoles of a dipole or poles of a dipole is called axial line. Then what is the potential due to a dipole on axial line? For point on the axial line, for point on axial line, theta equal to 0. That is angle between dipole moment and the point P. They are in the same direction, therefore theta equal to 0. And if the point lies opposite in this side to the dipole moment, then theta equal to 180 degree. Therefore, for a point on the axial line, there are two possibilities, theta equal to 0 and theta equal to 180 degree. And for theta equal to 0, then potential at point on the axial line, phi equal to theta equal to 0, cos 0 equal to 1, therefore phi equal to kp upon r square, or phi equal to minus kp upon r square. Because if theta equal to 180 degree, cos 180 equal to minus 1, hence it is minus kp upon r square, or we can write it as potential at point on the axial line, phi equal to plus or minus, it may be plus or minus 1 upon, here k equal to 1 upon 4 pi epsilon naught into p upon r square. And if the point lies on the bisector of the dipole, then theta equal to 90 degree. For point on the bisector or equatorial line, bisector, theta is equal to 90 degree. If theta equal to 90 degree, cos 90 equal to 0. Therefore, whole term becomes 0. Hence, potential at any point on the bisector of a dipole is equal to 0. And potential on the axial line may be plus or minus Kp upon r square or 1 upon 4 pi epsilon naught into P upon r square. Thank you. Contrast between potential due to a charge and potential due to dipole. It is potential, I write shortly, potential due to a charge and potential due to a dipole. Due to a dipole. Potential due to a charge is given by V equal to KQ upon R. That is, potential at a point due to a charge is inversely proportional to distance of the point and is directly proportional to magnitude of charge. As magnitude of charge increases, potential at that point increases. As the distance of the point increases, potential decreases or falls off as 1 upon R. Potential falls off as 1 upon R. And potential due to a dipole is given by V equal to Kp cos theta upon R square. And potential due to a dipole falls off as 1 by R square, or potential due to a dipole is inversely proportional to square of the distance. Therefore, potential due to dipole falls off readily than potential due to a charge. And potential due to a charge is inversely proportional to distance, and it is inversely proportional to R square. And potential at a point depends on the magnitude of charge, that depends on magnitude of charge. You may write that is small q or capital Q. Magnitude of charge and the distance of the point. But potential due to a dipole, it depends on the dipole moment P and angle between the line joining the point P and the dipole moment, and it is inversely proportional to square of the distance. And the potential due to a charge and a dipole is graphically represented as a graph of potential versus R. That is 1 by R for a charge and 1 upon R square for potential due to a dipole. And it is found that this is potential due to that is phi for charge, a single charge, and it is the line that is potential due to at infinity it is 0, and at a certain point the potential due to a charge and potential due to dipole, it is phi for dipole, and phi for dipole reaches rapidly to 0 because it is inversely proportional to R square, square of the distance, and potential due to a charge vanishes or decreases as 1 upon R, and this is vanishes as 1 upon R square. Clear? In next class we shall discuss potential energy due to a system of charges and superposition of potential.